So I graded question 3, if you did that, which was the machine with 2 states and 2 inputs, so a total of 8 state and input combinations. And if you have particular questions on that, I'm happy to talk about them, but I don't feel a need to go over at the details because most people did it exactly right or made minor mistakes transcribing from the K-mapper to the K-map and so on. But most people who did it seemed to do it perfectly correctly, which was awesome. A few things though, these were T flip-flops, not D flip-flops. Okay, so we use D flip-flops because they're pretty straightforward to fill in the inputs, but they could be T, they could be JK, could be a mix, and you gotta be careful which ones you're using based on the problem. The one hot encoding we talked about last time, but the idea was using 2 flip-flops even though there's only 2 states, and you have 2 possibilities for your state. And in each case, exactly one of the flip-flops will be hot, will be outputting a 1, right? And all the others will be outputting zeros. So in particular, this means there's 2 combinations of flip-flop values that we don't care about. And in practice, we might need to do something to make sure we don't accidentally end up in one of these states. Because if we don't care about it and we don't code it up, it's possible that if you end up in state 3, you just stay in state 3 forever. So we want a reset button or something that forces you into some initial state. But when you're filling out the table, right, you have 2 flip-flops, 4 combinations, 2 inputs. That's actually 16 rows of a transition table, but with a lot of don't cares. And so you can get some pretty reduced equations for your flip-flop inputs here. If you didn't do number 3, then I looked at number 1 and 2, and if those were good, then I gave you some points for those. And if you didn't do 1, 2, and 3, then you probably didn't turn it in, because I think everybody did one of them. So that was that homework. So any questions on that homework? All right, so questions on the lab. Yeah?
Can you show us how to reopen like a file after we've closed it?
Reopen.
Yeah, like just getting it to edit it.
So what system are you on?
I was doing it in the
In the collaboratorium? So those are Windows machines, and the most straightforward editor to use is just Notepad.
You have to save a notepad file.
So you are making a .v file, so you're sitting at a DOS prompt, right? And you can say Notepad experiment1.v, and it'll open a Notepad window and let you make changes and save them like that.
But wouldn't deep freeze affect those files if you wanted to come back to them at a later date?
So
Deep
if you log out, your files are gone, right? So you want to save it on a flash drive somewhere, right? And you can either CD into your flash drive and do your work right there, and then everything's going to be saved on your flash drive, or copy everything over before you exit and bring it all back. But once you've done this and you exit, you should have this file sitting in your current directory, and if you come back and you say Notepad, same file name, it should just open it up and let you continue where you were.
Couldn't you also just open up the file itself with actually going to the directory and double clicking to open it like that?
If on that system a .v file is set up to open with Notepad, sure. Or if you right click and go to properties and say open with, you can do that. The trick on these machines is that everything goes back to a default state. What did you call it, Craig?
Deep freeze.
Deep freeze, okay.
It wipes
So
the entire.
yeah, so every time you log off, log back in, it goes back to its original state. So anything that you set up is forgotten, right?
This is on my computer, right?
But on your computer, yeah, absolutely.
Gotcha.
Or if you have Notepad++, which I recommend, because Notepad's like 30 years old or something, but it still works. But Notepad++ is a more modern editor. It's actually an editor, and it does keyword highlighting. If it's a .v file, it knows it's Verilog, and so on and so forth. You had your hand up?
Yeah, I followed the steps for experiment 1, and when it says just hit go XP1.
Can't do that because there's no flash drive, right?
Okay.
Okay.
So we touched on this Thursday.
I recognize that there wasn't a flash drive. I didn't know
Yeah,
if you did the
so your way to do this right, so most of this works other than how you actually run the software. So C:\\. Did I Verilog or Icarus?
I Verilog.
I Verilog, okay, thank you. \bin I Verilog. That's the actual name of the compiler. Space -O space output name. This is what you want to call the compiled thing, space input name .v. So that's the file that you're editing. This will be the compiled version. And this is the compiler, and you're saying compile this input file, but call the output name. Okay, so the typical example would be all of this stuff, -O, experiment1, experiment1.v. And that'll create a file called exp1, which is the compiled version of your Verilog code. So how many people here have done 121, CSE 121? Okay, so this is like the GCC command, right? GCC-O output name input name.c. Exactly the same concept. It's a .v instead of a .c. If you don't do -O output name, you just say Verilog input file.v. It compiles it, and the output is called a.out, just like GCC. But then everything gets called a.out, and it gets confusing. So give it an output name. Okay, and then when you want to simulate it, iVerilog bin VVP. Whatever this output name was. So that, in some sense, runs the program for you. Okay, what it does is it runs a simulator that determines what your program will do.
I keep on getting a syntax error for the time scale. The first.
It's the tilde, not an apostrophe.
Yeah, it's in the
Ah.
upper left-hand corner.
Did I have a typo in there? Oh, no way.
It might just be the font.
Yeah.
I wasn't sure if it was
Looks like an apostrophe.
So that should be a back quote. Yeah, but it's making it fancy. That's a back quote, right? So,
So it's different key. So the
yeah. Right, so that's a back quote. So one of these, one of those, and it's usually it's like on the same key as the tilde for me.
just under the
But-
escape key.
Yeah,
Gotcha.
but it's the unshifted version of a tilde.
The input file, does it matter where that is saved?
As long as you tell the iVerilog command where it's saved, it doesn't matter. But if it's not in your current directory, you got to specify what directory it's in. Again, like GCC. Are you thinking of a subdirectory or? Okay. So if you make, let's say you open a DOS shell, and I don't have Windows booted up, otherwise we could do this. But you open a DOS shell, and it's like, C:\users /Enmacius, and I don't know what the prompt is, something like that. So if I say iverilog /bin /iverilog -o haha.v, right? It's looking for a file under users /Enmacius /haha.v. It's looking in my current directory, okay? And it's going to create an output file also in my current directory called haha. If I've got this file haha sitting on a flash drive, I could say something like, if my flash drive is on d:250 /haha.v. Right, now it's going to look on my flash drive in a directory called 250 for a file called haha.v. Right, but the other option is just type d:, and then current directory 250, and now I'm sitting in this directory, and my prompt is probably something like d:, /250 greater than. And if I've got my haha.v sitting in here, I can just do this line, and it'll read haha.v from here, and it'll place the output file in here also. And now you're using your own local hard drive, basically. So everything you do is going to persist, and just eject your drive when you're done. Put it back in when you want to continue. So DOS is kind of Linux-like in some ways, right? So CSE 121, you work on the CTEC server, right? That's Linux. It's kind of similar in some ways. And you've got current directories, and you can move around directories, and you can specify paths to things, and you type in commands. And this is basically saying this is the name of the program we want to run. That's the name of the compiler. But it's located on the drive C in a directory called iverilog and a subdirectory called bin. Right, so you're specifying a path name to it. And if you know DOS, you can set up an alias for this, right? Or make yourself a script. So you can just say compile haha, and it'll do this for you. And that's what I had on those flash drives, but I never made up those flash drives. So, but you can imagine that it's really convenient. So other questions on this? If you know how to set up your path on Windows also, right, you can just put this in your path, and the waveform simulator is this. Right, that's how we display the waveforms graphically. So if you were to put this and this into your system path, right, again like a path in Unix, then you can just say iverilog VVP and GTK wave. And that's what was supposed to get set up for you, but it didn't get set up. But you can go into your system properties and set your path variable if you know how to do that. And if I'm around and you want me to show you how to do this, I'm happy to do that. I just don't have Windows up here, so it's hard to go through it. So how many people got some sort of Verilog typed in and at least tried to compile it? Okay, good. That's encouraging. How many people feel like they can probably have some degree of success compiling this up with what we've talked about just now?
I get my GTK wave working.
You what?
I get the GTK wave working.
What's it do when you try to use it?
I'm assuming it's because I did not have this path.
Oh, okay.
So
Yeah. If you're at that point, you're past the worst of it, right? Because you've done the Verilog part, and you figured out the compile. Cool. Questions about this code? Yeah.
So I guess I'm just wondering, there's different ways to write the assigned statement.
Yes, there is. There are.
But it doesn't really affect the output.
Well, like what ways?
Well, if we do like we can write it based on the way that you showed us last time, where it's x equals select equals 0, then
Mhm.
it's either A or B.
Right, right.
Or you can write it with the actual equation.
Mm-hmm. Yeah, yeah. True. Okay, yeah, so perfect. There's multiple ways to do that. And as long as logically it evaluates the same thing, it's going to give you exactly the same result in the end. And that's kind of characteristic of programming languages too, right? We can write a program that reads 10 numbers and adds them together and calculates the average several different ways, right? We could take each number, add it to a running sum, and then at the end divide by 10. We could take each number, divide by 10, add it to a running sum. We could set the sum equal to the first number and then loop 9 times and read the other numbers and add them to the first, and so on and so forth. And logically you get to the same place. So one thing I want to talk about is this idea of test benches, because there's this instantiation here which we didn't really go through in a lot of detail on Thursday, and it's a little different from what we actually did in class. What we did in class was something like this. So here's an example of what we do. That is really faint. So we made a module called testbed. It had 2 registers that were inputs. It had a wire that was an output, and we set assign x equal to the sum of the inputs. And then over here in our initial statement, right, this is our one-time thing that's going to happen in the very beginning of the simulation. We said go ahead and set input 1 to 0, input 2 to 0, display the values of our input and output, and then set input 1 and input 2 to 1, and so on. Okay, that's different from what was going on over here in the lab write-up, where we kind of had 2 separate things happening. First, we had a module called exp1, right, which defines a module with 2 inputs, A and B, and output X, and does a logical AND. And that's the whole module, okay? There's no initial statement in here. There's nothing called a test bench in here. This is a block of Verilog code that creates a chunk of hardware for doing a logical AND. So the way this is written up in the lab, now we make another module, totally separate module called test bench. And test bench is what we're going to use to test that module exp1. Okay, and this all looks the same down here, the initial in 1 equals 0 and 2 equals and so on. The difference is what the test bench does is it creates an instance of exp1 called u1. Right? That's like the u1 in your wiring diagrams. So we're saying I want to make an instance of this module exp1 that we already defined. I want to call that instance u1, and I want to connect these variables here, in1, in2, and out, to the inputs and outputs of exp1. So exp1, right, the inputs are A and B, the output is X. So this line right here, this is saying I want to connect my variable in1 to exp1's A input. I want to connect my register into to EXP1's B input. I want to connect my wire out to EXP1's X output. And then everything else is basically the same. We give values to in1 and in2, and we look at this variable out. But this instantiation of EXP1 is a critical piece of Verilog, right? So the idea is we have EXP1. Right, system diagram. And we're creating a new module where we call it test bench. Test bench. And what is test bench? It's got, these are kind of internal. It's got an in1, an in2, and an out. And when we make that instantiate statement, what we're doing is we're saying I want to take EXP1 with A, B, and X, and I want to connect them like this. Is that clear? So we're making an instance of EXP1, we're calling it U1. And we're saying how we're going to feed the inputs and read the outputs. And then everything in this test bench initial statement is basically setting in1, in2, and looking at the value of out. Now, what we've been doing in class was we didn't put our inputs and outputs here. We made these things registers, and we took these assignment statements, and we put them in here, and said inside this module we're going to set in1 to this, in2 to that, and so on and so forth. But the right way to do it is what's in the lab here, right? Build your module that you want to test, and then put that inside a test bench. Stimulate the inputs, look at the outputs, see if it works. The ideas are, one, the test bench can be fixed, okay? It's just this block of code that's going to stimulate inputs, look at outputs in certain ways. The changes you're going to be making as you're debugging your system are in your module. So you go into the code for your module, you make some change, you rerun your test bench. It creates a copy of your module inside, drives the inputs, looks at the outputs, right? The other idea is that we could have multiple modules, and we bring them all together inside this test bench. We connect them all together to one another, and we do our input-output analysis. And ultimately, once we know that our module is working, we don't care about the test bench. We're going to take this module and we're going to say, okay, I want to program this programmable device, this FPGA, to implement this module, right? And if we have the test bench code embedded inside here, we've got to remove it, and it breaks things. So we're keeping the module separate and then putting it inside a test bench to test. But for quick and dirty development, we're just putting the stimulation of the inputs, the monitoring of the outputs inside this module itself, because it's quick and dirty. Okay, so experiment 2. How many people did something with experiment 2? At least scratched out some Verilog code, hoping to run it. If you didn't get to that point, any questions about this? Can you envision how you would do it? Right, and an assignment statement with that ternary operator is going to be useful. You can say see if select's equal to 1, and based on that, set this equal to either one thing or another thing. And that's basically what a multiplexer does. All right, so before we can implement the mood machine, we need to talk about this other aspect of behavioral Verilog, which is this event-based behavior that I alluded to on Thursday. So let's talk about that, and then we'll come back and look at how we implement an actual state machine. And it's a whole lot easier than what we've been doing on the boards when we do state machine analysis. or what you did in your homework. So we're inside a Verilog module, we're writing code, and we know what the assign statement does. Let's just refresh. So we've got input, variable name, we've got output, variable name. That's just naming the things that are in the argument list for the module and telling us which direction they go. You can also do bidirectional, but we don't need two-way ports right now. There's a wire statement. It's kind of optional, but it's nice to put it in anyway. It basically says that this variable is just a piece of wire. It can't remember anything, but we can use it to connect things together. We can also say something like wire bracket 3:0 variable, and that says variable is actually a bus of wires. In this case, a set of 4 wires, which we can refer to with variable 0, variable 1, and so on. So same as an array in programming language. And then there's this other one that we kind of slipped in there, which was register. And when we declare something to be a register, it's kind of like saying I want this to be able to remember a value. So we're usually making a flip-flop. And we can make an array of these the same way as we do with wires. But when you see reg, think flip-flop. It may not always be an actual flip-flop, but that's what you can have in mind. And then we had an assign statement. Let me not call it that. Let me just say left equals right. So we can have some expression on the right, and if we say assign left equals right, it says calculate, build some circuit to calculate that value on the right, take the output of it, run it along a wire, and feed it into this thing on the left, where this is usually going to be a wire. So that's pretty much what we've done so far with Verilog. And all the interesting stuff is kind of in this right-hand side of an assign statement. We can do logic, we can do addition, we can do multiplication, we can do ternary operators to do conditional things and make multiplexers and so on. So I want to introduce one more statement and then one thing that we do with that statement. So this is the keyword always. So what does always mean? It means always, right? At all points in time. So always we can use an at symbol to say at, something like pos edge, some variable. I gotta double check my parentheses because it's hard to write it. It's easier to type it. So always at pos edge some variable name. Never mind. Should be like this. Begin. And eventually end. Okay, here's what this statement means to Verilog. Remember, this is hardware we're building. It's not procedural code. Here's what this statement means. Build a piece of hardware so that whenever this variable goes through a positive edge transition, goes from a 0 to 1, all of this stuff happens. Build a piece of hardware so that whenever this variable changes from a 0 to 1, the stuff in this body happens. So do we know a piece of hardware that does something when a certain input changes from a 0 to 1?
Flip-flop?
Yeah, pretty much any flip-flop actually. if it's positive edge triggered and we look at the clock input, flip-flop does nothing until that clock input changes from a 0 to 1. So when we make an always statement, we're somehow asking the system to build some piece of circuitry that's going to involve flip-flops. And this is probably going to be connected to the clock input of those flip-flops. And what's going to happen here is somehow triggered by pulsing the clock on these flip-flops. Now, would it make logical sense to put an assignment statement in here? Probably not. Because assignment is saying connect a wire from the output of Y to the input of X. And this block would say whenever this input changes from a 0 to a 1, connect a wire from the output of Y to the input of X. And that's not how Verilog works. It can't make and break wires at runtime based on the values of inputs. So we don't want to use assignment statements in here. But here's what we can do. We can say copy the value of Y into X. And we have to use this special notation, this less than sign followed by an equals. It's like an arrow, right? So this would say whenever this variable changes from a 0 to 1, copy whatever the input of Y is, whatever the value of Y is, to X. So let's think about how we would do that. And suppose that's our whole always block. It's just that one assignment statement. Well, there's a piece of circuitry that will do what that assignment statement says. It says when this variable changes from a 0 to 1, this D flip-flop, its input on the clock is going to raise from 0 to 1. And what does the D flip-flop do when the clock raises? It looks at the D input and it loads that into its current value. So when the clock raises, whatever the value of Y is, that will become the value of this flip-flop, and that value comes out on the Q output, and that Q output is connected to X. So on the positive edge of this variable, X will take on the value of Y. And it happens at that moment. And a moment later, if I change the value of Y, that does not get copied to X. And this is fundamentally different from this. If I just have a module that says assign X equals Y, anytime Y changes, X is going to change to the same value. With this, that's not the case. Y can change 1,000 times and X is never going to change until the positive edge of this variable occurs.
So you can't have triggered assign statements?
You cannot have triggered assign statements, but the effect of this is exactly a triggered assign statement. But assign, actually, we can think of it as connect a wire from here to here. And we can't say, okay, break that wire, okay, put the wire back now. We can, but we don't. All right, so this one statement always block will give you a flip-flop circuit like this. And we want to understand this, but ultimately we're going to forget about this. And we're just going to think about always blocks. But to get to that point, we need to understand how this maps over to here. So let's try another one. And let me start putting in some more code here. So let's make X a register. And I'm going to use clock instead of VAR, because we usually think of these things as clocks. And clock can just be a wire. And let's say always at positive edge clock begin. X gets assigned the negation of X. So tilde X means complement in Verilog. So X is assigned its complement. So what could this look like in hardware?
There's no semicolon after begin?
No,
That
don't ask me why. Or after end.
sounds good.
So we're gonna have a D flip-flop. So what drives this input right here?
Clock.
That's the clock. Where's X located?
Q.
Q. But what feeds D?
Q.
X naught. It would probably just take the Q bar input, but either way, functionally, this is what that block will synthesize to. And this is a little state machine, right? This is the kinds of things that we were doing in chapter 5 when we were designing state machines. We have flip-flops, we have logic. The flip-flop feeds into the logic, the output of the logic feeds the inputs of the flip-flops, and we have clocks. I hope that stops quickly.
What's that squiggly next to that?
This,
Yeah.
that's negation.
Negation? Okay.
So a pipe is or, an ampersand is and a tilde is not.
Oh, okay.
Thank you. That's not significantly better. So we can design state machines using this idea of an always block. So let's make a toggle flip-flop. They always sound like they're having fun over there.
Some paper thin wall.
That's a divider, so you can actually open this up into a big room.
Oh, well, it is literally paper thin there.
Yeah. All right, let's make a toggle flip-flop. So what's a toggle flip-flop look like? What are the inputs and outputs?
1001.
Now what are the inputs and outputs called? T, good. What else?
T bar.
Q bar and Q. Okay, so I'm going to call this Q bar, like that. All right, and then what's the behavior of it?
It stays the same and toggles slow.
Exactly. So on the rising edge of the clock, if t is 0, the new value of q is the same as the old. If t is 1, the new value of q is the complement of the old. So that's the basic behavior. Well, let's just make a Verilog module for that. So we're going to make a t flip-flop. It's going to have a clock, a t, a q, and a q bar. So clock's going to be a wire. T is just going to be a wire, it's just an input. Output Q. And I'm going to make Q a register because we know a T flip-flop's going to have to, in some cases, remember what its previous value was, right? Or complement it and remember it. It's a memory device. So we're going to make that a register, and we're going to make Q bar we can actually make that a wire. We could make it a register too, but we'll see different ways to do this. Do we want a positive edge triggered or a negative edge triggered T flip-flop? We can do whatever we want. You want to do negative? So we'll say always at negative edge clock. And so this will be a flip-flop that looks like this. It's got a little bubble on the clock input. So at negative edge clock begin.
Unrelated, but is there any reason that a clock would switch which edge it's triggered on in the middle of the process?
Usually not,
Okay.
but it's possible. And there are things like double data rate memory DDR that actually triggers on both rising and falling edge, so that you get two triggers for the price of one, basically. So there might be something that could do that dynamically too. And you can make multiple always blocks. You could have one for positive, one for negative. Okay, so at the negative edge of the clock begin. So what are we going to do? If t equals 1, I don't know if I need it then. We're going to find out. We don't. If t equals 1, what do we want to do? We want to set q to its complement. So we'll say q gets assigned the negation of q. And so only change things if the t input is 1. And if the t input is 0, we don't have to do anything. We could say q gets assigned to q, but that doesn't accomplish anything, right? So really, we just need this one if statement. If t is 1, set q equal to the complement of q. And then another end statement to end the always block. So that's the one thing that happens on the falling edge of the clock. And I'm going to set q bar so it's always the opposite of q. And that I can do with an assign statement. Now I could also have done this in here. I could have said set q bar equal to not q bar, right? But since I know q bar is always the complement of q, I'm just going to hardwire it. So this will take q, run it through an inverter, feed that into a wire called q bar. And that's the end of our T flip-flop module. I'm going to add one more thing. I'm going to add a reset input here. The reason is that when we simulate this, sometimes the simulator will get confused because it doesn't know what the initial value of Q is. So Q will start off as undefined, and when we try to negate it, it'll still be undefined. Now in physical hardware, there's no such thing as undefined. It will be a 0 or a 1. We just don't know which. But for the simulator, it'll actually say this is undefined. So we're going to put a reset in here, and we're going to say if the reset is high when the clock drops, set the Q to 0. I probably have the syntax wrong, but if reset is 1, force Q to 0. Otherwise, if T is 1, set Q to the complement of Q. Otherwise, we don't do anything. Does that make sense? Alright, so we got clock, T, Q, Q bar. Let's add our reset. So we got reset clock, T, Q, and Q bar. Alright, so we need a test bench. So we're going to drive the reset line, the clock line, and T. And we're going to look at Q and Q bar. So this is a T flip-flop. And so we're constructing a module and we're connecting to it. Yeah.
When you're naming our flip-flops, when it's T above,
Mm-hmm.
does it know what that means? Or is
No,
it just for readability?
that's just looking at this. I created a module, I named it TFF. Could have called it anything.
Gotcha. I wasn't sure if it was in like a library or not.
No, it's pretty uninformed about what's going on.
Okay.
All right, so let's take a 5-minute break. Let me type in some code here so you don't have to sit here and watch while I type. And then we'll go ahead and simulate this. And then we'll start digging deeper into the always statement. And then we'll go back and look at how to do state machines.